The universe is hiding something from us, not in the shadows of distant galaxies or the depths of black holes, but in the very fabric of space itself. Something invisible, something mysterious, is pulling the cosmos apart faster than we ever thought possible. Scientists call it dark energy, and it's the greatest unsolved puzzle in modern astronomy. But here's the thing. Dark energy isn't just some abstract force. It weaves through the universe like an unseen spiderweb, connecting everything in a vast, invisible structure known as the cosmic dark energy web. And this web, it's full of secrets, 25 mind-bending mysteries, to be exact, each one more fascinating than the last. Picture this: every second, the space between galaxies stretches wider, not because of gravity, but because of something far stranger. Imagine an entire cosmic architecture hidden in plain sight, dictating how the universe grows, evolves, and even how it might one day end. We're talking about forces so powerful they defy our understanding, structures so immense they dwarf the largest superclusters, and questions so profound they keep astronomers awake at night. What is this mysterious web made of? Why does it seem to grow stronger over time? And most chilling of all, could it hold the key to the ultimate fate of everything? This isn't just science fiction. It's the cutting edge of discovery, where the rules of physics bend and the universe reveals its most guarded enigmas. Over the course of this journey, we'll unravel 25 of these cosmic riddles, from the eerie voids where galaxies refuse to form, to the bizarre particles that might be dancing through the web's invisible threads. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The cosmic dark energy web isn't just out there, it's part of the story of us. And it's time to uncover its secrets. The first mystery of the cosmic dark energy web begins with a revelation so shocking it rewrote the textbooks. In 1998, astronomers made an observation that turned our understanding of the universe upside down. They weren't looking for dark energy, they were simply measuring distant supernova, the explosive deaths of massive stars, but what they found defied all expectations. These cosmic beacons weren't just moving away from us as the expanding universe predicts. They were speeding up. The universe wasn't just growing, it was stretching apart faster and faster, as if some invisible hand were pushing it. This wasn't just unexpected, it was impossible. Gravity, the force that binds galaxies together, should have been slowing the expansion, not accelerating it. The only explanation, a mysterious repulsive force stronger than gravity itself, woven into the fabric of space. Scientists called it dark energy, and its discovery sent shockwaves through physics. But here's the twist: this wasn't the first time this force had been theorized. Decades earlier, Albert Einstein had stumbled onto the same idea. He called it the cosmological constant, a mathematical fudge factor he added to his equations to keep the universe static. When Edwin Hubble proved the universe was expanding, Einstein dismissed it as his greatest blunder. But now it turns out he might have been right all along. So what is dark energy? Is it really just Einstein's cosmological constant, a property of empty space itself, where even a vacuum hums with latent energy? Or is it something far more bizarre? Some theories suggest it could be a dynamic field, changing over time. Others propose it's evidence of extra dimensions or even flaws in Einstein's own theory of gravity. But the most unsettling possibility, that dark energy isn't constant at all, that it's growing stronger. If true, it could mean the universe is headed for a fate more extreme than anyone predicted. A big rip where even atoms are torn apart. One thing's certain, dark energy isn't just a footnote in cosmology. It's the dominant force in our universe, making up nearly 70% of everything that exists. And yet, after decades of study, we still don't know what it is. That's the heart of the first mystery, not just the force itself, but why it remains so stubbornly hidden. The cosmic dark energy web has just begun to unravel, and already it's pulling us deeper into the unknown. If gravity is the glue holding the universe together, dark energy is the cosmic blowtorch melting it apart. This brings us to the second great mystery of the cosmic dark energy web: why the universe's expansion isn't just winning against gravity, but absolutely crushing it. Think of it like an endless arm wrestling match where one competitor keeps getting stronger while the other weakens. Gravity pulls galaxies inward, but something out there is yanking space itself outward with relentless, growing force. Here's the strangest part: gravity works as expected everywhere we look. It keeps planets in orbit, binds stars into galaxies, and even creates the colossal filaments of the cosmic web. Yet on the largest scales, it's as if the rules suddenly flip. The space between galaxy clusters stretches faster than gravity can compensate, like trying to hold two ends of a rubber band while someone keeps pulling. This isn't just expansion, it's accelerated expansion, growing more extreme with time. To grasp how bizarre this is, picture inflating a balloon. Normally, blowing air in would slow as the balloon stretches tighter. But what if the balloon started inflating faster on its own, the rubber thinning until pop? That's essentially the Big Rip scenario. If dark energy's push keeps intensifying, it wouldn't just separate galaxies, it would shred stars, planets, and eventually space-time itself down to the subatomic level. But why does dark energy overpower gravity? One theory suggests it's baked into the vacuum of space itself, an inherent energy that grows as the universe expands. Another proposes that gravity might leak into extra dimensions at cosmic scales, weakening its grip. The most unsettling possibility: dark energy isn't just constant, it's evolving, growing denser as space stretches, like a shadow that darkens the more light you shine on it. Whatever the answer, this cosmic tug-of-war sets the stage for an even deeper mystery. What happens when the web's threads finally snap? The cosmic web isn't just a backdrop for galaxies, it's a living, breathing structure, sculpted by forces we can't see. This brings us to the third spine-tingling mystery of the cosmic dark energy web: its invisible architecture. Picture the universe as a colossal sponge, with galaxies clustered along gleaming filaments, separated by unimaginably vast voids. These filaments aren't random. They're the highways of the cosmos, built by gravity over billions of years. But here's the twist: dark energy is the silent architect, stretching this web into existence while simultaneously tearing it apart. How does it work? Imagine a river carving a canyon. Gravity pulls matter into dense strands, forming the web's skeleton. But dark energy is the floodwaters, widening the gaps between those strands, accelerating the emptiness until the voids dominate. Supercomputer simulations reveal this eerie dance: galaxies huddling along gossamer threads, while the spaces between them grow ever larger, like cracks in drying mud. The result: a universe where less than 5% of everything, stars, planets, us, is made of stuff we actually understand. The rest, a staggering 95%, is dark energy and dark matter, the universe's hidden scaffolding. And that's where things get truly bizarre. These voids aren't just empty, they're actively repulsive. Dark energy pushes them outward, creating cosmic dead zones where galaxies rarely form. Some are so vast they could swallow thousands of Milky Ways side by side. Meanwhile, the web's filaments grow thinner, stretched like taffy by the accelerating expansion. If this keeps up, future astronomers might peer into the sky and see only darkness, the last galaxies vanishing over the horizon of space itself. What's even stranger: we don't just see this web, we feel it. Earth isn't stationary, it's being gently tugged toward the Great Attractor, a mysterious gravitational anomaly in the web's depths. But here's the kicker: dark energy's push will eventually overpower even these titanic pulls, leaving galaxies stranded in isolation. So is the cosmic web destiny, or a fleeting moment in the universe's life? Simulations hint at an unsettling truth: This intricate structure is temporary. As dark energy tightens its grip, the threads will snap, the voids will merge, and the universe will transform into something unrecognizable. The web we see today, it's just a single frame in a much darker film, one where the credits might roll on everything we've ever known. For decades, scientists assumed dark energy was as steady as the ticking of a cosmic clock, a relentless, unchanging force woven into the fabric of space itself. But what if that's not the whole story? The fourth mystery of the cosmic dark energy web challenges this very assumption, raising a tantalizing question. Could dark energy be evolving? Einstein's cosmological constant, the idea that empty space holds a fixed, immutable energy, once seemed like the perfect explanation. It was elegant, simple, and mathematically clean. But the universe rarely follows the rules we write for it. Enter quintessence, a theory that turns dark energy into something far more dynamic. Imagine not a static force, but a swirling, shifting field that ebbs and flows like an invisible tide. This isn't just theoretical speculation. Observations of distant quasars, the brilliant cores of ancient galaxies, hint that dark energy's strength might have changed over billions of years. Some datasets suggest it was weaker in the past, as if the universe's expansion had a slow start before hitting the accelerator. The implications are staggering. If dark energy isn't constant, it could mean our universe's fate isn't set in stone. A cosmological constant leads inevitably to a cold, lonely end, galaxies drifting apart until the last stars fade. But quintessence opens wilder possibilities. What if dark energy grows weaker over time, allowing gravity to regain control, or worse? What if it surges unpredictably, hurling the cosmos toward a cataclysm we can't yet foresee? The debate is far from settled. Some cosmologists argue the quasar data could be statistical noise, while others see the glimmer of a paradigm shift. One thing's certain, if dark energy is dynamic, we're not just deciphering the universe's expansion, we're reading its mood swings, and that changes everything. Deep in the cosmos lies an emptiness so vast, it defies comprehension, a yawning chasm where galaxies should be, but aren't. This is the fifth enigma of the cosmic dark energy web, the unsettling mystery of supervoids. Take the Boötes void, a cavernous darkness stretching 330 million light-years across. To put that in perspective, if the Milky Way were a grain of sand, the Boötes void would be the size of a football stadium, with just a handful of galaxies scattered inside. It's not merely empty, it's aggressively empty, as if something carved out the universe's scaffolding and left a gaping hole. But how do voids this colossal even form? The standard model of cosmic structure predicts that gravity should have pulled matter into a web-like pattern, with galaxies clustered along filaments and modest voids between them. Instead, we find these staggering deserts of space, far larger than theory allows. The culprit, dark energy. As it accelerates the universe's expansion, it stretches these voids wider, like invisible hands pulling apart taffy. The voids aren't passive leftovers, they're growing, their emptiness magnified by dark energy's relentless push. Now, here's where it gets truly strange. The cosmic microwave background, the afterglow of the Big Bang, holds a peculiar anomaly, a cold spot roughly in the direction of the Boötes void. Normally, temperature fluctuations in the SIMB are tiny, the result of density variations in the early universe. But this spot is too cold, as if the light passing through the void lost extra energy on its way to us. Could this be dark energy's fingerprint? One theory suggests supervoids act like cosmic funnels. Photons entering them lose energy climbing out of the void's weakened gravity, a phenomenon called the integrated Sachs-Wolf effect. But the cold spot's size and chilliness push even this explanation to its limits. Some researchers propose an even wilder idea, that the cold spot isn't just a void but evidence of a collision with another universe, a bruise left by a cosmic sibling in the multiverse. Others argue it's a statistical fluke, a trick of perspective. But if dark energy truly is sculpting these voids into unnatural sizes, it raises a chilling question. Are we seeing the first signs of the cosmic web's unraveling? Because here's the truth about voids: they're not just empty space. They're battlegrounds where dark energies push overwhelms gravity's pull, where the universe's expansion isn't just happening but accelerating. And if the voids keep growing, their edges will one day be the only places left where galaxies still cling together, the rest an endless expanding darkness. The cosmic dark energy web isn't just hiding in the voids, it's writing the universe's obituary in them. If the universe is a battlefield, then dark energy and dark matter are locked in an eternal tug of war, one pushing, the other pulling, with galaxies caught in the middle. This brings us to the sixth enigma of the cosmic dark energy web, the cosmic rivalry between these two invisible giants. Dark matter whispers to galaxies, holding them together with unseen hands, while dark energy shouts into the void, wrenching them apart. Take galaxy rotation curves, for example. Stars orbiting a galaxy's edge move way faster than they should based on visible matter alone, the only explanation. A halo of dark matter, its gravity gripping those stars like an invisible leash. Without it, galaxies would fling themselves apart. Yet dark energy counters this stability on a grander scale, stretching the space between galaxy clusters so fast that gravity struggles to keep up. Then there's the bullet cluster, a smoking gun for this cosmic duel. When two galaxy clusters collided, their visible gas clouds slammed together, glowing hot. But the bulk of their mass, revealed by gravitational lensing, sailed right through untouched. That missing mass, dark matter, barely interacting with anything but gravity. Meanwhile, dark energy wasn't just absent. It was working in the background, ensuring the voids between such clusters grow ever wider. So here's the million-dollar question: could these rivals be secret collaborators? Some theories suggest dark energy and dark matter might be different faces of the same unknown physics, a single shadowy force that repels at cosmic scales but clumps locally. Others propose dark matter decays into dark energy over eons, slowly tipping the balance. One thing's certain: this isn't just a struggle for the universe's fate. It's a clue that we're missing something fundamental, a hidden chapter in the laws of physics. And until we solve it, the cosmos will keep its greatest secrets locked in this invisible duel. Somewhere in the depths of space, a clock is ticking, but no one can agree on how fast. This is the seventh mystery of the cosmic dark energy web, the Hubble tension crisis, a cosmic whodunit where the universe's expansion rate seems to change depending on who's measuring it. Picture two detectives examining the same crime scene, each convinced the evidence tells a radically different story. On one side, we have meticulous observations of nearby supernova and Cepheid variable stars, celestial yardsticks that let us gauge the universe's current expansion. On the other, the cosmic microwave background, a pristine snapshot of the infant universe from 13.8 billion years ago. Both methods are rock solid in their own right. Yet they stubbornly refuse to agree on how quickly space is stretching apart. The numbers tell the tale. Measurements based on today's galaxies suggest the universe expands at about 73 kilometers per second per megaparsec, meaning a galaxy 1 megaparsec away recedes at 73 kilometers per second, 2 megaparsecs at 146, and so on. But the CMB, echoing the universe's first breaths, insists the rate is closer to 67. That 6-kilometer gap might seem trivial, but in cosmology, it's a chasm. It implies that either our tools are flawed, our theories are missing something monumental, or the universe itself has been secretly changing the rules. Dark energy sits at the heart of this puzzle. If it's truly a constant force, as Einstein's cosmological constant suggests, these measurements should converge. But what if dark energy isn't playing fair? Some theorists propose it might have shifted strength over cosmic history, stronger in the past to match the CMB, weaker now to explain the supernova data. Others wonder if we're seeing hints of exotic particles or even modifications to gravity itself. Then there's the unsettling third option, that there's no tension at all, just hidden errors in our observations. But after decades of cross-checking, that possibility grows slimmer by the year. Here's where it gets truly mind-bending. The Hubble tension isn't just an academic debate, it's a potential window into physics beyond our current understanding. If dark energy's influence fluctuates, it could mean the universe's fate is far stranger than we've dared to imagine. Or perhaps the cosmos is layered with unseen forces, like an orchestra where dark energy is just one instrument in a much wilder symphony. One thing's certain, until we solve this discrepancy, the cosmic dark energy web remains a tapestry with threads we're only beginning to unravel. There's a number in cosmology so bizarre, it keeps physicists staring at their whiteboards in disbelief. It's not some abstract equation or a distant galaxy's redshift, it's a simple ratio, a cosmic coincidence so precise, it feels like the universe is playing a trick on us. Right now, as you watch this, the energy density of dark energy and the energy density of matter are almost identical. Not off by a factor of 1,000 or 1,000,000, but within spitting distance of each other. And that's not just odd, it's statistically impossible unless something deeper is at work. This is the eighth mystery of the cosmic dark energy web, the why now. Problem, think of it like this: dark energy's strength doesn't fade as the universe expands. It's constant, a fixed amount of energy in every cubic centimeter of space, no matter how much that space stretches. Matter, on the other hand, thins out as the cosmos grows. Back when the universe was smaller, matter's density was overwhelming, like a packed concert crowd. Dark energy, a whisper lost in the noise. Fast forward billions of years, and space has ballooned so much that matter is now sparse. Its density diluted while dark energy's relentless push remains unchanged. By sheer chance, we happen to live in the exact sliver of cosmic time where the two densities are nearly equal. It's as if we woke up to find the ocean's waves perfectly matching the height of a sandcastle on the one day we decided to build it. So is this really a coincidence, or is it a clue? One camp argues it's pure luck, a fluke of timing that lets us exist to ponder it, but others sense something more profound. What if dark energy isn't static but adapts to the universe's conditions? Some theories, like the tracker field model, suggest dark energy's density could have followed matter's lead, adjusting its strength over eons to match it at a specific moment. Even wilder is the anthropic principle, the idea that universes with different dark energy ratios might not support life at all. In that case, we're here because the numbers line up, a cosmic selection bias. Then there's the elephant in the room, the universe's age. 13.8 billion years isn't just a random number, it's the exact timescale needed for dark energy and matter to reach this precarious balance. Coincidence, or the signature of a deeper law, one that ties dark energy's behavior to the very ticking of the cosmic clock? If true, it would mean the universe isn't just expanding, it's unfolding on a schedule we're only beginning to decode. The why now problem isn't just academic, it cuts to the heart of whether the cosmos is governed by random chance or hidden symmetries, and until we solve it, we're left with a haunting thought: the universe didn't have to be this way. So why is it there's a ghost in the equations of physics, a number so catastrophically wrong? It threatens to unravel everything we know about the universe. This is the ninth mystery of the cosmic dark energy web, the quantum origins of dark energy, and why the math behind it might be the most embarrassing failure in scientific history. According to quantum theory, empty space isn't empty at all. It's a seething foam of virtual particles, pairs of matter and antimatter that blip in and out of existence so fast we can't detect them directly. But their energy leaves a fingerprint. If you could add up all these fleeting quantum fluctuations, they should fill the vacuum of space with a colossal energy density. a background hum so powerful it ought to warp the cosmos beyond recognition. Here's the problem. When physicists actually crunch the numbers, they get a value for this vacuum energy that's 10 to the power of 120 times larger than the measured strength of dark energy. That's a 1 followed by 120 zeros. To call this a discrepancy is like saying the Pacific Ocean is slightly damp. It's not just wrong, it's disastrously wrong, the kind of miscalculation that would get you laughed out of any other field. Yet quantum mechanics and general relativity, the twin pillars of modern physics, both insist this absurd number should exist, so why doesn't the universe reflect it? One possibility is supersymmetry, a hypothetical framework where every particle has a hidden twin. If true, these shadow particles could cancel out the vacuum's excess energy, leaving just the faint whisper we observe as dark energy. But after decades of searching, no supersymmetric particles have turned up at the Large Hadron Collider, leaving the theory on shaky ground. Another wild card, extra dimensions. If gravity leaks into unseen spatial dimensions beyond the 3 we experience, it could dilute vacuum energy's effects, masking its true strength. Yet the most unsettling answer might be that we're asking the wrong question entirely. Maybe dark energy isn't tied to quantum vacuum fluctuations at all, but something entirely separate, an unknown layer of reality we haven't even glimpsed yet. Or worse, what if the math isn't broken and we're missing a universe where these unimaginable energies do exist, leaving ours as a bizarre outlier? Either way, the gap between prediction and observation isn't just a technical hiccup. It's a screaming alarm that somewhere, buried in the cosmic dark energy web, lies a truth so profound it could rewrite physics itself. And until we solve it, we're stuck with the most humbling thought of all, that the universe's greatest force might also be its greatest joke. What if dark energy isn't just a silent force in the background, but a ticking time bomb, gaining strength with every passing second? This brings us to the 10th and perhaps most terrifying mystery of the cosmic dark energy web: phantom energy, a theoretical form of dark energy so volatile it could rip the universe apart atom by atom. Imagine a rubber band stretched tighter and tighter until it snaps. Now replace the rubber band with spacetime itself, and you've got the nightmare scenario cosmologists call the Big Rip. The idea hinges on a single, chilling variable, dark energy's equation of state, a number representing how its pressure relates to its density. If this value dips below -1, meaning dark energy's repulsive push grows stronger as space expands, it triggers a feedback loop of cosmic horror. Space doesn't just expand, it accelerates uncontrollably like a car with a stuck gas pedal. First, galaxy clusters are torn apart, then galaxies, then stars. In the final moments, even atomic bonds would shatter, leaving the universe as a cold, lifeless sea of isolated particles. But is this just a theoretical doomsday, or could it be real? Observations of Type Ia supernova, the same cosmic mile markers that reveal dark energy's existence, hint at something unsettling. Some datasets suggest dark energy's equation of state might indeed creep toward that catastrophic threshold. Yet galaxy surveys paint a murkier picture, with large-scale structures appearing more stable than phantom energy predicts. It's as if the universe is whispering 2 conflicting prophecies, one of violent dissolution, the other of gradual decay. The stakes couldn't be higher. If phantom energy exists, it would mean the universe's fate isn't just cold and empty, it's violent. But here's the twist. Even if the Big Rip isn't real, the mere possibility forces us to confront how little we understand about dark energy's true nature. Because whether it's a constant force or a growing menace, one truth remains: we're dancing on the edge of a mystery that could redefine existence itself. Hidden in the faint glow of the cosmic microwave background, the oldest light in the universe, lies a series of cryptic fingerprints. These aren't just random wrinkles in the fabric of space-time. They're the 11th mystery of the cosmic dark energy web, echoes of dark energy's presence from the universe's infancy. Think of the CMB as a cosmic baby picture, snapped when the universe was just 380,000 years old. Yet even then, dark energy was already leaving its mark, subtly warping the patterns we see today. The Planck satellite, a high-precision observatory designed to map this ancient light, revealed something astonishing. The universe is geometrically flat to an eerie degree, like a perfectly stretched sheet with no curves or warps. But here's where dark energy enters the scene. For the universe to be this flat, it must have undergone a turbocharged expansion in its first moments, cosmic inflation followed by a mysterious slowdown, and then, billions of years later, a re-acceleration driven by dark energy. The CMB's temperature fluctuations, those tiny hot and cold spots, act as a cosmic barcode. When scientists scanned them, they found statistical anomalies, subtle dips and peaks that don't quite match predictions. Some of these quirks, like the infamous cold spot, align eerily with regions where dark energy's influence would have subtly bent the CMB's light over billions of years. But the real shock came when researchers compared the CMB's large-scale patterns with modern galaxy surveys. The two datasets disagreed on how much structure exists in the universe. The CMB suggests matter should be more clumped than what we observe today, as if something has been smoothing out the cosmic web over time. That something could be dark energy, acting like an iron over cosmic wrinkles, stretching the universe so fast that gravity can't keep up. Now the million-dollar question: was dark energy always there, lurking in the background, or did it switch on at a specific moment in cosmic history? Some models suggest it might have played a role even during inflation, the universe's explosive first moments. Others propose it emerged later, like a dormant gene suddenly activating. The Planck data adds fuel to the fire. Its measurements of the universe's expansion history show odd fluctuations that hint at dark energy's dynamic nature. What's clear is this: the CMB isn't just a relic. It's a palimpsest, a cosmic document where dark energy's signature has been scribbled over and over, waiting for us to decode it. And until we do, we're left staring at the universe's oldest light, wondering what other secrets it holds. Galaxies aren't just drifting apart in the cosmic expansion, they're rushing as if pulled by something beyond the edge of the known universe. This is the 12th mystery of the cosmic dark energy web, the baffling phenomenon of large-scale flows, where entire clusters of galaxies stream toward invisible attractors at speeds that defy dark energy's uniform push. Imagine throwing confetti into the air, only to watch it not just fall, but race in unison toward some unseen magnet. That's what astronomers observe when they map the motions of thousands of galaxies, a coordinated movement so vast it spans billions of light years, as if the universe itself were tipping toward a hidden weight. The most notorious of these flows is the so-called dark flow, first detected in 2008 by studying the peculiar velocities of galaxy clusters. These clusters aren't just receding with the expansion of space, they're also drifting in the same direction at breakneck speeds, as fast as 600 miles per second. What's stranger, the direction points toward a patch of sky devoid of any known superclusters or massive structures. It's like watching a flock of birds suddenly veer toward an empty field, ignoring all visible landmarks. So what's tugging them? One radical theory suggests the flow might be the gravitational imprint of a universe that existed before ours, a relic structure from a time before the Big Bang, lingering like a shadow at the edge of space-time. Others propose it could be the pull of a neighboring universe in the multiverse, its gravity leaking through the fabric of our own. Both ideas sound like science fiction, but here's the kicker: they're mathematically plausible within certain models of quantum cosmology. Yet dark energy complicates the picture. If it uniformly accelerates expansion, why hasn't it erased these flows entirely? Some researchers argue the answer lies in the cosmic dark energy web's uneven texture. Dark energy might dominate the voids, but in regions where matter is densely woven into filaments, gravity could still hold enough sway to orchestrate these colossal motions. It's a cosmic tug of war where the rope itself is stretching, yet the teams keep pulling. Then there's the unsettling alternative, that dark energy isn't as uniform as we think. Could pockets of varying dark energy density create hidden gradients, warping spacetime in ways we haven't yet detected? If so, these flows might not be anomalies at all, but signposts to a deeper layer of the universe's architecture. One where dark energy and gravity aren't just competing, but collaborating in ways we've yet to comprehend. Whatever the truth, the dark flow forces us to confront an unnerving possibility, that our universe isn't the solo act we thought it was. Something vast, something ancient, maybe even something other, is out there pulling strings we're only beginning to sense. And until we trace that pull to its source, the cosmic dark energy web remains a tapestry with threads leading beyond the edges of our imagination. What if everything we thought about dark energy was wrong? Not just slightly off, but fundamentally mistaken, a cosmic mirage painted by our own incomplete understanding of gravity. This is the 13th mystery of the cosmic dark energy web, where a rebellious faction of physicists dares to ask, could dark energy be an illusion? The idea starts with a simple observation. Einstein's theory of general relativity has ruled cosmology for over a century, predicting everything from black holes to gravitational waves. Yet when it comes to the universe's accelerating expansion, it requires us to conjure an invisible, unmeasured force, dark energy, to make the equations work. That's like blaming ghosts for a door slamming shut rather than checking for a draft. Some researchers argue we're not seeing a new force at all, but the limits of Einstein's theory itself. Enter modified Newtonian dynamics, or a radical rewrite of gravity's rules. Instead of invoking dark energy, man tweaks gravity's behavior on colossal scales, suggesting it weakens differently than relativity predicts. Imagine gravity as a radio signal. In the cosmic hinterlands, it might crackle and fade, mimicking the effects of an outward push we've mislabeled as dark energy. But man isn't the only challenger. Another school of thought proposes that the universe isn't as uniform as we assume. If matter is clumped into sprawling, uneven megastructures beyond our observational horizon, their gravitational pull could warp our measurements, creating the illusion of acceleration. Picture standing in a valley surrounded by mountains you can't see. The slopes distort your perception, making the horizon seem to rise when it's actually level. Similarly, hidden cosmic terrain might trick us into seeing expansion where none exists. These theories aren't without flaws. Man struggles to explain the cosmic microwave background's precise patterns, while inhomogeneous models require matter distributions that border on the contrived. Yet they're gaining traction precisely because dark energy remains so elusive. After decades of searching, we've never directly detected it, only inferred its existence from cosmic side effects. That's left the door open for heretics to argue we're chasing a phantom, patching over gaps in our knowledge with a placeholder we don't fully understand. The stakes couldn't be higher. If dark energy is real, it reshapes our universe's destiny. If it's an illusion, we might be standing at the brink of a scientific revolution, one that forces us to rip up Einstein's rulebook and start anew. Either way, the question lingers: are we deciphering the cosmos's deepest secret or falling for its greatest trick? When astronomers first measured distant supernovae to trace the universe's expansion, they expected to see these stellar explosions dimmer than nearby ones, but not this dim. The discrepancy was slight, just a fraction of a percent, but it was enough to rewrite cosmology. These weren't just dying stars, they were cosmic signposts revealing dark energy's grip on the cosmos. But what if the signposts are misleading us? The 14th mystery of the cosmic dark energy web asks a haunting question. Are supernovae truly fading because of accelerating expansion, or could something else be stealing their light? Take the case of Type Ia supernova, the standard candles of cosmology. These explosions occur when white dwarf stars steal enough mass from a companion to trigger a runaway thermonuclear detonation. Because they peak at a predictable brightness, scientists use them to gauge cosmic distances. But distant supernovae appear fainter than their redshift suggests, as if the universe stretched faster than expected during their light's journey to us. That's the cornerstone of dark energy's case, yet loopholes lurk in the details. One culprit could be interstellar dust. Over billions of years, galaxies accumulate cosmic grime, tiny particles that scatter and absorb light. If early universe dust is more pervasive or differently textured than we've accounted for, it might dim supernova without dark energy's involvement. Some studies suggest certain types of dust could mimic the faintness signature, like fog obscuring a streetlight's true intensity. Then there's the evolution problem. Type Ia supernova aren't all identical. Their explosions depend on the chemical makeup of their progenitor stars. Early universe stars had fewer heavy elements, meaning their supernova might have burned slightly differently, perhaps peaking fainter than their modern counterparts. It's like comparing two light bulbs, one made with vintage tungsten, the other with modern LED. If we assume they're identical, we'll misjudge the distance to the older one. But the most unsettling possibility is that we've misread the cosmic tape measure itself. Calibrating supernova distances relies on a chain of assumptions, from the brightness of Cepheid variable stars to the Hubble constant's value. A kink anywhere in that chain could skew the results. Recent debates over the Hubble tension highlight how fragile these measurements can be. So where does that leave dark energy? Even if dust or stellar evolution plays a role, neither fully explains the supernova data's consistency across different surveys, yet the doubt lingers like a shadow. If future telescopes spot a supernova in a pristine, dust-free void or catch an ancient explosion defying the faintness trend, it could shake cosmology to its core. Until then, the missing supernova remain both dark energy's strongest evidence and its most vulnerable thread. And in science, the most tantalizing mysteries often hide in the gaps between what we see and what we assume. The universe's first moments were a spectacle of unimaginable violence, a runaway expansion so fast, it makes today's dark energy-driven acceleration look sluggish. This was cosmic inflation, a fraction of a second when space itself ballooned from smaller than an atom to the size of a galaxy cluster. And here's where the 15th mystery of the cosmic dark energy web gets spine-tingling. What if dark energy isn't the universe's first dance with anti-gravity? What if inflation was just Act 1 and dark energy is Act 2? The parallels are too striking to ignore. Inflation was driven by a mysterious field, often called the inflaton, whose repulsive gravity stretched space exponentially. Then, as abruptly as it began, inflation switched off, leaving behind the hot, dense plasma of the Big Bang. Fast forward 13.8 billion years and another repulsive force, dark energy, takes center stage, accelerating expansion once again. Coincidence, or could these bookends of cosmic history be linked? Some theorists propose a breathtaking idea. That dark energy isn't new at all, but a relic of that primordial inflationary field. Perhaps it never fully vanished, just faded into the background, lying dormant until the universe grew sparse enough for its effects to re-emerge. Picture a dormant volcano, silent for eons until shifting pressures awaken it anew. In this scenario, dark energy isn't an intruder in the cosmos. It's the echo of the universe's birth, a whisper from the very first instant, but there's a wilder twist. If inflation could restart in patches, a theory called eternal inflation, then our universe might be one bubble in a frothing multiverse, each with its own dark energy quirks. Even more radical is the idea of cyclical cosmology, where dark energy isn't the end but a reset button. In these models, the universe's accelerating expansion eventually triggers a new Big Bang, birthing another cosmos from the ashes of our own. It's a cosmic phoenix rising again and again in an endless loop. the evidence, faint but tantalizing. Certain anomalies in the cosmic microwave background, like large-scale temperature asymmetries, hint that inflation might not have been uniform. Could these be scars from an earlier cycle, or signs of dark energy's precursor stirring in the infant universe? Future gravitational wave detectors might hunt for primordial ripples that could distinguish between these theories. One thing's certain: if dark energy and inflation are two faces of the same cosmic force, it would mean the universe is playing a far grander game than we've glimpsed. Not just expanding but breathing, not just evolving but recycling, and somewhere in that vast rhythm, the answer to dark energy's greatest secret might be written in the first trillionth of a second of time itself. What if everything we see, every galaxy, every star, even the fabric of space itself, is nothing more than a cosmic projection, a shimmering mirage painted onto the surface of some unimaginable boundary? This is the 16th mystery of the cosmic dark energy web, a radical idea that dark energy might not live inside our universe at all, but on its edges, a holographic whisper from the void. The holographic principle, born from the fiery paradoxes of black hole physics, suggests a universe where reality is fundamentally two-dimensional. All the information we perceive, from the motion of planets to the glow of distant quasars, could be encoded on a distant surface, like a cosmic DVD projecting its contents into the volume we call home. At first glance, it sounds like science fiction, but here's where it gets eerie. This principle might solve one of dark energy's deepest puzzles: why its measured energy is so absurdly tiny compared to quantum theory's predictions. Picture a black hole's event horizon, that point of no return where gravity's grip becomes eternal. According to physicist Jacob Bekenstein, the maximum entropy, the information capacity of any region of space, isn't determined by its volume, but by the area of its boundary. It's as if the universe were a library where books can't be stacked endlessly inward. Instead, every shelf's contents are written on its walls. Now stretch this idea to the cosmos itself. If our universe has a boundary, even an abstract one, its total information could be encoded there, with dark energy's value capped by the entropy limits of that surface. That's exactly what physicist Raphael Bousso proposed. Dark energy's feeble strength might reflect the universe's maximum information density, a cosmic pixel limit that keeps vacuum energy from exploding to quantum theory's catastrophic predictions. In this view, dark energy isn't a fluke or a tuning error. It's a signature of a deeper truth, that reality is a hologram and its projection has rules. But how does this holographic leash actually work? One clue lies in the interplay between gravity and quantum mechanics. In certain models, the negative pressure of dark energy emerges naturally from the universe's boundary dynamics, like tension in the skin of a balloon. Another wild possibility: that our three-dimensional universe is a shadow cast by processes unfolding in a higher dimensional space, a cosmic silhouette where dark energy is the faint glow of the projector's lamp. Skeptics argue this is all speculative math with no experimental hooks. Yet remarkably, the holographic principle predicts dark energy's observed value within striking range, something no other theory has managed. Even stranger, it aligns with the "why now" coincidence. As the universe expands, its boundary grows, subtly adjusting the pressure we perceive as dark energy. It's as if the cosmos isn't just expanding, but recalculating its own rules in real time. So are we living in a hologram? The answer might lie in the cosmic microwave background's faintest patterns, anomalies that could reveal the pixelation of spacetime itself. Until then, one thing's clear: dark energy's mystery isn't just about what fills the universe. It's about whether the universe as we know it is even truly there. The cosmic microwave background should be the ultimate equalizer, a near-perfect snapshot of the universe's infancy, glowing with nearly identical temperature in every direction. But when scientists peeled back the layers of this ancient light, they found something that shouldn't be there: a spine-chilling alignment dubbed the axis of evil. This 17th mystery of the cosmic dark energy web isn't just a statistical fluke. It's a cosmic curveball that threatens to upend our most sacred assumption about the universe, that it's the same in all directions. Here's the problem. When researchers mapped the CMB's temperature fluctuations, they expected randomness, a symphony of hot and cold spots with no discernible pattern. Instead, the data revealed a bizarre correlation. The largest scale fluctuations align eerily with two unexpected reference points, the plane of our solar system and the direction of Earth's motion through space. It's as if the universe's oldest light is whispering that our corner of the cosmos holds special significance, a heresy against modern cosmology's cornerstone principle of isotropy, the idea that the universe has no preferred direction or center. So what's really going on? One camp dismisses it as a cosmic coincidence, a trick of perspective akin to seeing faces in clouds. But the odds of such an alignment happening by chance are staggeringly low, less than 1 in 1,000. Others suggest more unsettling explanations. Could dark energy be unevenly distributed, like fog thicker in some valleys than others? If so, its repulsive push might vary across space, subtly warping the CMB's patterns along hidden fault lines. Or perhaps the axis of evil is a relic of pre-Big Bang physics, a scar from some primordial asymmetry that seeded the universe with a silent bias, the darkest possibility. That we're seeing evidence of a multiverse bump, the gravitational imprint of a neighboring universe brushing against ours in the cosmic foam. In this scenario, dark energy's apparent uniformity might be an illusion, masking pockets of varying strength where universes collide. It's a radical idea, but the axis of evil's persistence has forced even skeptics to grudgingly admit the cosmos might be playing favorites. Until we solve this anomaly, one humbling truth remains. The universe we see, the one we've built our theories upon, might be stranger, messier, and far less uniform than we ever dared to imagine. And if dark energy is part of that asymmetry, its greatest secret might not be how it pushes the cosmos apart, but where it's pulling us from. Dark energy might seem like an unchanging force, a constant hum in the fabric of space, but what if its strength has been shifting over cosmic time? This 18th mystery of the cosmic dark energy web dives into a startling possibility. That dark energy isn't just accelerating the universe's expansion, but evolving with it. Recent galaxy surveys hint that its influence wasn't always dominant. In fact, around 5 to 6 billion years ago, dark energy might have been weaker, lurking in the background while gravity still ruled the cosmos. So what flipped the switch? The evidence comes from painstaking observations of galaxy clusters, the universe's largest gravitationally bound structures. By measuring how these clusters grow and merge across different eras, astronomers can reconstruct the tug-of-war between gravity's pull and dark energy's push. Here's the twist. Clusters from around 5 billion years ago appear more tightly packed than current models predict, as if gravity's grip was stronger back then. It's like finding fossilized ripples in a pond that suggest the water was once calmer, before some unseen force began stirring it. If dark energy truly was weaker in the past, it raises a profound question: why now? Why did it surge to dominance just as Earth and our solar system were forming? One theory points to the universe's changing density. In the early cosmos, matter was packed tightly, its gravitational pull overwhelming dark energy's faint nudge. But as space expanded and matter diluted, dark energy's constant presence finally tipped the scales. Think of it like a seesaw early on. Matter's weight kept it grounded, but as matter's side grew lighter, dark energy's subtle force lifted it skyward. Yet another idea is far more radical. That dark energy isn't tied to empty space at all, but to a dynamic field that strengthens or weakens over time. Some models, like quintessence, propose this field could have phases like water freezing into ice or boiling into steam, triggering shifts in its repulsive power. If so, the universe's acceleration might not be a one-way street. dark energy could wax and wane in cycles as unpredictable as the weather. The implications are staggering. If dark energy's strength is a moving target, the universe's fate might not be set in stone. A future surge could tear apart galaxies prematurely. A decline might let gravity claw back control. But the real puzzle remains: what cosmic hourglass is dark energy watching, and when will it decide to flip again? Somewhere out there, beyond the edges of our cosmic horizon, an infinity of other universes might be lurking, each with its own laws, its own physics, and its own version of dark energy. This 19th mystery of the cosmic dark energy web takes us down the rabbit hole of the multiverse, where our universe's oddly life-friendly dark energy might not be a fluke, but a cosmic lottery ticket we just happen to win. String theory, the framework that tries to unite all forces of nature, paints a surreal picture of reality. Instead of one universe, it predicts a vast landscape of possible universes, maybe 10 to the power of 500 of them, each with different constants, dimensions, and even different strengths of dark energy. In most of these universes, dark energy is either so weak it's irrelevant or so strong it tears space-time apart before stars can form. Yet here we are, in a universe where dark energy is just strong enough to accelerate expansion, but just weak enough to allow galaxies and life to exist. That's no small coincidence. If dark energy were a few notches stronger, galaxies would never have clumped together. A little weaker, and gravity would have crushed the cosmos back into a big crunch long before life had a chance. This razor-thin balance is called the Goldilocks problem, or why is our dark energy just right? One controversial answer: we're in a bubble universe, one of countless others where the dice rolled differently. Most universes might be barren, but in ours the numbers lined up perfectly. Think of it like a cosmic game of Russian roulette. The multiverse is the revolver, with most chambers holding a bullet, a dark energy strength too extreme for life. But we pulled the trigger and somehow landed on the single empty chamber. This idea, known as the anthropic principle, suggests that dark energy's value isn't fine-tuned for us. We just happen to live where it could support us. But not everyone buys the multiverse as a get-out-of-jail-free card for fine-tuning. Critics argue it's an untestable excuse, a way to dodge the deeper question: is there a fundamental reason dark energy is this specific value? Some theories, like the relaxation model, propose dark energy could have dynamically adjusted during the universe's infancy, settling into its life-friendly state like a ball rolling to rest in a valley. Others suggest dark energy isn't random at all, but tied to an undiscovered symmetry in the laws of physics. The wildest twist: if we're in a multiverse, the cosmic dark energy web might not even be ours. It could be the gravitational shadow of a neighboring universe pressing against ours, its influence leaking through the cracks of space-time. Some versions of string theory allow for this kind of interaction, parallel universes brushing close enough to nudge each other's physics. If true, dark energy wouldn't just be a mystery, it'd be a message from a world we can never see. So is the multiverse the answer, or just another layer of the puzzle? Until we find hard evidence, a statistical anomaly in the CMB, an impossible void, or a gravitational wave from beyond our cosmic bubble, it remains a tantalizing what if. But one thing's certain: if dark energy truly is a multiverse artifact, it means our universe isn't special. It's just lucky, and that changes everything. Black holes are cosmic enforcers, bending space-time to their will except when it comes to dark energy. This 20th mystery of the cosmic dark energy web pits two titans of physics against each other in a paradox that defies logic. How do black holes keep growing in an accelerating universe, seemingly untouched by the very force tearing everything else apart? On one side, dark energy stretches space itself, diluting matter and pushing galaxies apart. On the other, black holes gain mass as the universe expands, feasting on the cosmic background radiation and even vacuum energy itself. It's as if you blew up a balloon while someone inside kept getting heavier. How the answer might rewrite our understanding of both dark energy and singularities. Enter the black hole quintessence hypothesis, a daring idea that black holes don't just ignore dark energy but consume it. Imagine a sponge in an ocean. As the water level rises, the sponge soaks up more, growing denser while the sea around it thins. Similarly, if black holes absorb dark energy instead of repelling it, their event horizons could swell even as the universe's expansion accelerates. This isn't just theoretical sleight of hand. Recent studies of supermassive black holes reveal their masses are larger than expected for their age, as if they've been scarfing down extra helpings of spacetime's hidden energy. But here's where it gets surreal. If dark energy fuels black holes, it could mean singularities aren't just gravitational dead ends, but cosmic recyclers converting repulsive energy into mass. That challenges Einstein's field equations, which treat black holes as static vacuum solutions, indifferent to the universe's expansion. Some theorists suggest this might hint at a deeper link between quantum mechanics and gravity, where dark energy's properties are altered near event horizons. Picture a river hitting a whirlpool. The current's flow changes dramatically at the edge, creating a zone where the usual rules don't apply. The implications are staggering. If black holes truly interact with dark energy, they could be the universe's dark energy sinks, slowing its acceleration in localized pockets while growing monstrously large over time. Future observatories like LISA might detect this by spotting anomalies in black hole mergers, where the resulting singularity's mass doesn't match predictions. Yet the paradox cuts deeper. If black holes do absorb dark energy, why hasn't the universe's expansion slowed in regions packed with them? And if they don't, how do they keep gaining mass in a cosmos where everything else is thinning out? The answer might lie in the quantum foam at a singularity's edge, a place where dark energy isn't just a force but a menu item. Until we solve this, one thing's clear: the dance between black holes and dark energy isn't just a curiosity. It's a showdown between the universe's two greatest mysteries, and the outcome could rewrite physics itself. Neutrinos are the ghosts of the particle world, ethereal, nearly massless, and so elusive that trillions pass through your body every second without a trace. Yet these cosmic phantoms might be hiding a secret far darker than we imagined. The 21st mystery of the cosmic dark energy web asks a question that blurs the line between the infinitesimal and the infinite. Could neutrinos be whispering to dark energy itself? For decades, neutrinos were thought to be massless, zipping through the universe at the speed of light. Then came the bombshell discovery that they do have mass, just vanishingly small, like a feather's weight compared to a mountain. But here's the twist: that mass might not be constant. Some theories propose that neutrinos could interact with dark energy's underlying field, their weight shifting as the universe expands. Picture a chameleon changing colors to match its surroundings, except here, the chameleon is a fundamental particle, and its color is its mass, tuned by the invisible hand of dark energy. This isn't just wild speculation. Observations of cosmic neutrinos, those relic particles from the Big Bang still drifting through space, show anomalies in their energy distribution. Some appear heavier than expected when traced back to earlier cosmic epochs, as if they were carrying extra mass that faded over time. One explanation: a dark energy field that permeates the cosmos, subtly tweaking neutrino properties as it stretches spacetime. It's like finding a trail of footprints that change depth halfway, hinting at hidden quicks and beneath the surface. Then there's the neutrino portal hypothesis, a daring idea that neutrinos could be the only particles sensitive to dark energy's hidden dimensions. While the rest of matter ignores dark energy's pull, neutrinos might dip in and out of its influence, acting as cosmic messengers between our world and whatever lurks beyond. If true, studying neutrinos could be like holding a flashlight to dark energy's shadow, revealing its contours for the first time. The implications are staggering. If neutrinos and dark energy are entangled, it would mean the universe's largest force is chatting with its shyest particle, a conversation we've been deaf to until now. Future experiments like Dune and Hyper-Kamiok could catch these ghostly particles in the act, their mass fluctuations betraying dark energy's fingerprints. Until then, one thing's clear: the answer to dark energy's greatest riddle might not lie in the vast emptiness of space, but in the fleeting weight of a particle that barely exists. The universe is playing a vanishing act, and dark energy is the magician pulling the strings. This 20-second mystery of the cosmic dark energy web reveals a chilling illusion. As space stretches faster than light can traverse it, galaxies are disappearing from view, not by fading, but by being yanked beyond the edge of our perception. Imagine standing in a hall of mirrors where the reflections don't just distort, they sprint away, vanishing one by one until you're left staring only at your own lonely silhouette. That's the future dark energy is crafting for cosmologists. Right now, we can observe galaxies billions of light years away, their light finally reaching us after eons of travel. But dark energy's accelerating expansion means that over time, light from distant galaxies will never reach us at all. Their photons, fighting against the stretching of space itself, will eventually lose the cosmic race, redshifting into oblivion. The result, a universe that seems emptier, not because galaxies are vanishing, but because they're being dragged over a horizon we can never cross. Future astronomers might peer into deep space and see nothing. No distant quasars, no ancient supernova, not even the cosmic microwave background, just an inky void where the cosmos once teemed with light. This is the end of cosmology scenario, a future where the universe's expansion erases the very evidence of its own history. Billions of years from now, civilizations might arise in galaxies like our Milky Way, look up at the sky and conclude they're alone in a static island universe. The ironclad proof of the Big Bang, the redshift of galaxies, the afterglow of creation, will have receded into unreachable darkness. Dark energy won't just shape the universe's fate, it will rewrite its story, leaving only fragments of the truth behind. But here's the twist: this illusion isn't just a distant threat, it's already begun. The most distant galaxy we've spotted, GNZ 11, is so far away its light has traveled 13.4 billion years to reach us. Yet, due to the universe's expansion, it's now actually 32 billion light-years from Earth and receding faster every second. We're witnessing it in its infancy, but its present-day form is forever beyond our grasp. With each passing moment, more galaxies slip over this horizon, their light stretching into wavelengths too faint to detect. The implications are staggering. If dark energy continues unchecked, the observable universe could shrink to include only our local group of galaxies, bound together by gravity's last stand. Everything else lost to the void. We might be living in a golden age of cosmology, uniquely positioned to glimpse the universe's full grandeur before the curtains close. Future scientists could inherit a sky barren of clues, forced to reconstruct cosmic history from echoes we take for granted today. So is this truly the universe's fate, or just another layer of the illusion? Some models suggest dark energy's strength could peak and wane, leaving pockets where light still connects. Others hint that civilizations might find workarounds, exploiting quantum entanglement or gravitational waves to see beyond the horizon. But one thing's certain: dark energy isn't just expanding the cosmos, it's editing it in real time, and we might be the last generation to read the full story. Quantum entanglement is one of the weirdest phenomena in physics, a ghostly connection where particles millions of miles apart instantly mirror each other's states, as if space and distance don't exist. But what if this spooky action at a distance isn't confined to the tiny realm of particles? The 23rd mystery of the cosmic dark energy web dares to ask: could entanglement be scaling up, stitching the universe together on a cosmic level? And could dark energy be its signature? At the quantum scale, entangled particles defy common sense. Measure one, and its partner snaps into a correlated state faster than light could travel between them. Einstein called it spooky, but today we know it's real. Now, a fringe group of physicists is proposing something even more radical. That entanglement doesn't just link particles, it weaves space-time itself. In this view, dark energy might not be a force or a field, but the leftover fabric of quantum connections stretched across the cosmos. Think of it like a cosmic spiderweb, where every strand is an entangled bond, vibrating with latent energy as the universe expands. The math behind this idea is as elegant as it is controversial. Certain loop quantum gravity models suggest that space-time emerges from a network of entangled quantum bits like pixels on a cosmic screen. As the universe grows, these entangled links stretch thin, their tension manifesting as the repulsive push we call dark energy. It's not a perfect analogy, but imagine stretching a rubber sheet covered with glued-on springs. The springs resist, creating an outward pressure, not because something's pushing, but because the connections themselves are straining. Then there's the experimental smoke. In 2016, a team at the University of Chicago reported something bizarre. Entangled particles in the lab seemed to respond to the local curvature of space-time, as if gravity and entanglement were whispering to each other. Even stranger, calculations suggest that if enough particles entangled across vast distances, their collective spookiness could warp space-time on large scales, mimicking dark energy's effects. Critics dismiss this as speculative sleight of hand, pointing out that no known mechanism scales entanglement to galactic proportions, but supporters counter that we've barely scratched quantum gravity's surface. After all, if black holes can erase information via entanglement, as Hawking radiation hints, why couldn't the universe itself store energy in entangled bonds? The implications are dizzying. If dark energy is quantum entanglement writ large, it would mean the universe isn't just expanding, it's remembering. Every galaxy, every star, every atom might be linked by invisible threads of quantum connection, fraying as space stretches, their tension driving the acceleration we can't explain. Future quantum gravity probes or even tabletop entanglement experiments might look for this cosmic fingerprint, an energy too diffuse to see, but woven into the structure of reality itself. One thing's certain, if entanglement and dark energy are entwined, we're not just decoding the universe's expansion, we're reading its deepest, most hidden conversation. For centuries, physics has operated under the assumption of four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But dark energy's stubborn refusal to fit neatly into this framework has led to a radical rethink. What if there's a fifth force at play, one so cunning it hides in plain sight? This 24th mystery of the cosmic dark energy web dives into the realm of chameleon particles, hypothetical entities that could rewrite the rules of the cosmos by masquerading as dark energy while evading detection where matter is dense. The chameleon theory proposes an exotic scalar field permeating the universe, whose strength shifts depending on its surroundings. In the void between galaxies, it exerts a repulsive push, mimicking dark energy's accelerating effect. But in dense regions like Earth or laboratory vacuums, the field cloaks itself, weakening its influence to near undetectability, hence its namesake. Picture a cosmic chameleon changing colors, vibrant red in the emptiness of space, but fading to transparent when surrounded by matter. This behavior isn't just poetic, it explains why we've never measured this force locally. While dark energy's effects dominate the vast cosmic web, chameleon particles could be lurking in every lab experiment, their presence masked by the very equipment designed to find them. Scientists are hunting these elusive fields with experiments of breathtaking precision. The Earth Wash Group at the University of Washington uses torsion balances, delicate devices that measure twist caused by minuscule forces, to search for deviations from Newtonian gravity in vacuum chambers. If a chameleon field exists, its strength should fluctuate between the chamber's high and low density regions, subtly tugging on the balance. Meanwhile, at CERN CAST experiment, researchers beam particles through intense magnetic fields, watching for anomalies that might betray a chameleon's whisper-thin interaction with matter. The stakes couldn't be higher. If confirmed, chameleons wouldn't just explain dark energy, they'd upend particle physics. Unlike conventional forces mediated by particles like photons or gluons, a fifth force might operate through entirely unknown mechanisms, perhaps tied to higher dimensions or quantum gravity. Some models even suggest chameleon fields could screen gravity itself, offering an alternative to dark matter by modifying how gravity behaves on cosmic scales. Yet the chameleon remains stubbornly invisible. Null results from experiments like Adelberger's torsion balances have tightened the constraints on where or if such a force could hide. Critics argue the theory is too flexible, tweakable to fit any observation. But proponents counter that absence of evidence isn't evidence of absence. We might simply need more sensitive tools. Future experiments like upgrades to the Action Dark Matter experiment could probe the chameleon's predicted parameter space with unprecedented precision. What makes this mystery so tantalizing is its duality. Dark energy could be both a cosmological constant and a local phantom, its effects scale-dependent. The universe's acceleration might not stem from one monolithic cause, but from a menagerie of interconnected phenomena, with chameleon particles as just one player in a far grander drama. Until we trap this cosmic shapeshifter in a lab, one truth remains. The forces we've always known might be sharing the stage with an actor we've yet to see. The universe's final act might not be a slow fade to black. It could be a dramatic encore. The 25th and ultimate mystery of the cosmic dark energy web forces us to confront two opposing visions of existence's end. One where dark energy leads to eternal silence, and another where it becomes the spark of cosmic rebirth. On one side lies the heat death, a chilling scenario where space expands until every star burns out, every black hole evaporates, and the universe reaches absolute zero, a frozen graveyard of scattered particles too distant to ever interact again. But there's a twist. Some theorists argue dark energy's grip could loosen over trillions of years, allowing gravity to resurge and pull everything back into a fiery collapse. Others propose something even wilder, that dark energy isn't the end but the prelude to a new beginning. Picture a pendulum swinging through time. In cyclic models like bounce cosmology, dark energy's acceleration isn't permanent. It's just the universe stretching to its limit before snapping back in a cataclysmic reversal. Recent supercomputer simulations show how a universe saturated with dark energy could reach a critical point where quantum corrections to gravity kick in, halting expansion and triggering a big bounce. Instead of a singularity, the collapse leads to a rebound, a new Big Bang birthing another cosmos from the ashes of our own. It's not science fiction, the math checks out. In these models, dark energy is the universe's reset button, its repulsive push ensuring the collapse doesn't stop at a black hole-like crunch, but rebounds with enough force to birth a fresh universe. The evidence hidden in the cosmic microwave background, certain anomalies like large-scale temperature fluctuations that defy standard inflation, could be scars from a previous cycle, echoes of a universe that existed before ours. Even more tantalizing are hypothetical relic gravitational waves, ripples in spacetime that might carry fingerprints of a pre-bounce era. Future observatories like the Big Bang Observer could hunt for these whispers from a time before time. Yet the heat-death scenario remains equally plausible. If dark energy's strength is truly constant, or worse, grows unchecked, the universe faces a lonelier fate. Galaxies will vanish over the horizon, their light stretched beyond detection. Black holes will decay via Hawking radiation, their mass evaporating into photons that redshift into nothingness. The last sentient beings, if any remain, will gaze into an abyss where not even the memory of stars survives. So which is it, endless ice or eternal return? The answer might hinge on dark energy's deepest secret, whether it's a static force or a dynamic one, a cosmic constant or a phase in a grander cycle. Either way, the cosmic dark energy web isn't just shaping the universe's present. It's scripting its finale and possibly its next opening act. From the baffling acceleration of the universe's expansion to the eerie whispers of phantom energy, these 25 mysteries of the cosmic dark energy web don't just challenge our understanding, they rewrite the very narrative of reality. We've peeled back layers of the cosmos to uncover voids so vast they defy logic, entangled particles that might stitch space-time together, and black holes that grow despite the universe's relentless stretching. Each revelation isn't just a puzzle piece, it's a door swinging open to questions we never thought to ask. Dark energy isn't just a force, it's the universe's most brilliant storyteller, spinning tales of multiverses, holograms, and cycles of cosmic rebirth. But here's the most humbling truth of all: for every answer, a dozen new mysteries emerge. The more we learn, the clearer it becomes that dark energy isn't just part of the cosmos, it's the stage, the director, and the script all at once. It molds the cosmic web, dictates the fate of galaxies, and might even hold the key to what came before the Big Bang. And yet, after decades of searching, we still don't know what it is. That's the beauty of science. The universe guards its secrets fiercely, revealing them only to those who dare to keep looking. So now it's your turn. Which of these 25 mysteries pulls at your curiosity the most? Is it the chilling possibility of the Big Rip, the ghostly tug of the dark flow, or the spine-tingling idea that we're living in a hologram? Drop your thoughts in the comments. We're just getting started. Because while dark energy might be stretching the universe apart, it's also drawing us closer to truths we've yet to imagine. And in future videos, we'll dive even deeper into the enigmas hiding in the shadows of space. Stay curious, the cosmos has only begun